Yeah, so we are from the University of British Columbia. UBC, for those of you who don't know, is sits on the peninsula at UBC in Vancouver, British Columbia. And we have around 60,000 people on campus per day. Floor area, does anybody have that stat?
I'm going to go old school. It's 9 million square feet, roughly. 9
million square feet. So we're roughly the size of a small city here.
Sorry, that's just 4 buildings, and then there's an additional 8 million in housing. Sorry.
8 million in housing and 9 million in core. Our group, Energy and Water Services as a whole, was initiated in 2014. Our group consists of 5 BMS techs, the BMS manager, Zach here, 4 energy conservation engineers, a data analyst specific position, myself, the energy conservation manager, and then Philip, who both Zach and I report to, who runs the energy conservation and innovation group. Our goals here, so our goals are basically to offset growth. So I'll go back to the first one. We have built a SkySpark database, for those of you who don't know, where all of our buildings' BMS systems get imported into for data analytics. And we leverage that for Campus as a Living lab to support academic research. And we also use it to run our energy conservation projects. Our group has targets of 4 gigawatt hours of electricity per year and 20,000 gigajoules of natural gas. And those are our energy conservation targets for the campus for our group. And that was basically set to offset campus growth because UBC, it's joked that another acronym for that is that we're the University of being constructed because the university never stops building. And so that's our energy use. So those targets were set to offset that growth. And while our campus has grown over 500 square meters since 2000, campus energy and emissions have not. So we have actually proven that we've been able to offset this growth. And we've essentially decoupled UBC's energy consumption and emissions from our campus growth. Since 2000, UBC's energy management and conservation projects have decreased electricity consumption on campus by 55 gigawatt hours and around 557,000 gigajoules annually. This is our overall energy story for the campus. As you can see on the left here, this is the campus energy in gigawatt hours. The different colors represent different energy sources that feed our district energy system and our electricity consumption on campus. And on the right here, we have campus floor area. So you can see as our campus floor area has increased by about 500,000 square meters, our energy consumption has actually decreased or stayed the same. And I don't know how much time I have to go into detail here, but in the early 2000s, we had an eco-trek project which initiated the campus energy conservation. They did a lot of things to get the ball rolling for us, like install energy meters on all of our buildings, do lighting projects, simple scheduling.
And VAV
retrofit, yeah. In 2014, our department was established and we took it from there by decreasing the energy use. In 2015, we came up with the 2020 Climate Action Plan to also address our emissions for 2020 and continue energy conservation on campus. So this is the big picture here. Cumulative energy and water savings since the very beginning in EcoTrek, we've saved the university about $90 million in fiscal year 20 through energy conservation. This includes electrical, gas, and water, and it's projected to keep increasing if we keep going forward targets. So how do we do this? How do we get here? And I'd like to take one of our best examples of how we did this and dive into the details a little bit here. Life Sciences Center is our largest building on campus, And we've shown that we have achieved a 45% reduction in building energy use through low or no cost energy conservation measures. And I'm going to try to get through most of this to tell you how we did that. But the big picture of this building in particular, it was originally designed to consume only 300 kilowatt hours per meter squared. But when it started operating in 2020, it consumed over twice that much energy, sitting up around 800 kilowatt hours per square meter of building floor area. And throughout the last 10 years, we've decreased its energy use intensity by roughly 45% by getting it down to $840,000 per year of energy consumption. I'm just gonna see if I can hide this here so I can see my notes. What does this building look like? It was the first LEED gold building on campus, completed in 2004. It's the largest research and teaching building on campus, consisting of 560,000 square feet. It has an animal care area and a level 3 biohazard lab. It is roughly 4% of campus space and 10% uses 10% of campus energy, and was using twice as much more than modeled. HVACs, we had 34 air handling units, 10 exhaust systems, 28 high plume exhaust fans, around 780,000 CFM of makeup air. That's actually quite a bit light. It's more like 1 million. And 12 to 14 air changes in lab to begin with. The plant summary, we have 380 ton screw chillers, a glycol heat recovery system that recovered heat from exhaust air to preheat coils in the large air handling units, and high temperature heating. It was originally on a steam system that we had at UBC, and a low temperature reheat. So that was 2 6,000 pound per hour steam heat exchangers and 1,000 kilowatt plate and frame hex for condenser water heat recovery. And this was the original design. So scratching the surface for our department, when we started looking at this, our department relied on consultants heavily to discover energy savings opportunities. And we put it through the building tune-up program, or the continuous optimization program here, which is incentivized by BC Hydro, our electricity utility provider. And this program did some very initial savings with less than a 1 year payback through outdoor air lockout, weather predictions, scheduling adjustments, and a domestic hot water optimization. And it saved roughly 3,600 gigajoules per year, 300 megawatt hours per year, and roughly 3% right off the bat. The next thing we did is a coil cleaning program, and we did this not just in life sciences, but we did this campus-wide throughout all of our large air handling units. So we hired some cleaners to come in and clean the coils, remove the mold and bacteria, dirt and leaves, decomposed filter media. It was pretty grimy looking. This also had a less than 1 year payback and is recommended every 5 years. So I think it's been around 10 years, and we are just looking at doing this again. And our original M&V showed that we saved roughly 400 megawatt hours per year, 1% of the building's energy consumption. And this is through reduced static pressure drop, basically, and allowing for increased heat exchange from the coils. Yeah,
No, you're gonna talk about filters.
Yeah, and so we also changed the filters. So 2 filters before, we had a MERV 8 and a MERV 13, and then we moved to 1 filter after, so MERV 14 mini pleat filter with gaskets. And the reason for this is it required less filter changes to change 1 filter rather than 2. It reduced sort of waste in inventory and reduced energy, and this saved roughly 336 megawatt hours per year.
Also had us ready for COVID when it arrived.
Also had us ready for COVID when it arrived. Good one, Zach. So digging a deeper from 2010 onwards, we had a dedicated energy management team. I think we had 2 people in energy management in 2020. And the first thing that was noticed is that the cooling tower was rejecting heat in the middle of the winter. Roughly 1 megawatt of waste heat from life sciences cooling tower was rejected out of the building on a typical day. For those of you just looking into these things, if you have LEED buildings, they often have a waste heat energy recovery from the cooling systems, and they often are not commissioned to work properly. So this is a really easy one to find. Is your cooling tower running in the middle of winter? Ask yourself that question and you will be very surprised at how often you're rejecting heat when you shouldn't be. So this is a simplified chilled water schematic for the building. These are the 3 chillers. This is the chilled water line, and this is the condenser water loop that rejects heat out of the cooling towers. There is a heat recovery hex here that was supposed to be recovering heat to the heating water line. But when we looked into it, what we found is that the temperatures were set so that you could never, it wouldn't have been possible to actually reject heat into the heating water line of the building, because the temperature that it was set at for the supply water temperature was just too high that you couldn't bring heat over from the condenser water loop to that side. Hopefully I'm not going through this too fast. And then the other problem we found was that there was a manual bypass that was 50% open. So even if we wanted to change the temperatures and lower the return water temperature from the building, we had to close this bypass in order to actually force flow through this heat exchanger. We were also able to increase the condenser water temperature on our BMS system. And so then we were able to reject heat into the heating water system. So we decreased the heating water supply by about 10 F, which then decreased the return water temperature and also increased it on the condenser water side so we could actually reject heat. And what we found here was—
We also discovered that it was piped incorrectly, that it was parallel flow. You showed it. I don't know if you talked about it.
No, I didn't.
There was a note on your slide.
It was an odd install issue where the contractor installed the exchanger, kind of reducing its efficiency or effectiveness because they had piped it parallel flow rather than counterflow, which is typical. Counterflow is a typical installation. So the expense of reversing that in a running building was quite complex. So
looking at the results of that, the baseline energy use is the dotted line here, what it was doing before, and then post-fix is the line afterwards. So you can see that during the nighttime or daytime, I'm not sure which that is, it's actually recovering a lot of heat. And this saved roughly 15,000 gigajoules per year, almost 10% of the building's energy use, just by getting that heat exchanger working. The next thing we did here, how am I doing for time? We optimized the chilled water system on campus, or sorry, in the building. So we have 3 chillers, and 2 of them would run at about 70% load. And we averaged a COP of 3. The supply water temperature was around 4.4 C, returning at around 9.4. And this is what we were running at in the winter. And what we were able to do is we found that these chillers like to be loaded up, and we can increase the efficiency when we do that. So by increasing the supply water temperature from 5 to 7.2 C and returning at 11, we were able to increase the COP of the chiller to 5 and run only 1 versus 2 of them. So that was increasing the supply water temperature on the chilled water side. And the results for this saved around 1,300 megawatt hours per year, 3% of building energy use. And you can see the before and after here on the electrical demand from the supply water temperature reset. So that was our department scratching the surface in 2010 to 2013. And then we started really getting a better understanding of what the building, how the building operated through those initial measures and gaining more confidence in our ability to change how the systems operate. So digging even deeper into this building, we had a look at the heat recovery potential in the building. So this is a graph of the heating load in the building in red, and then the cooling load in the building in blue. And so despite the improvements made to date, we found there was still a significant opportunity to recover waste heat from the cooling system. So there's roughly 500 kilowatts of base load cooling, and the heating demand around half a megawatt. So we put together a project with help and incentives from our gas provider, FortisBC, to implement a dedicated heat recovery chiller in this building. And so we added, in addition to this HEX, we added a heat recovery chiller to bump up the temperature of the condenser water loop to inject more heat into the supply water, heating water for the building. And this resulted in 10,000 gigajoules of natural gas savings, had fairly negligible electrical effects, and a 5-year payback without incentives. One of the next optimizations that we've done on campus to a number of buildings, not just life sciences, is looking at our high plume exhaust fans. So in this building, we have 28 high plume exhaust fans, and these are designed for the worst case wind scenario and high plume scenario. And we hired a company to do airflow testing with our buildings, and they actually built a 3D model of the campus, which I used to have a picture of in here that I took out. And they put it through wind tunnel testing to optimize how high we actually needed that plume to go to exit safely and not mix with intake air on the surrounding buildings. And for those of you that are not familiar with how these, what are these? Strobics, sorry. Well, how the strobics work is that there is a huge amount of bypass air that is just being sucked through them, that's actually not coming from the building at all. It's coming from outdoor air, and it mixes with the laboratory air and ejects at a much higher CFM and height than is needed for our particular campus. So what we were able to do is we are able to modulate and close the bypass dampers and reduce the speed that the high plumes are operating at based off of the sequences that the company that did the wind tunnel testing provided to us. The other thing we did is that only 2 of the 3 fans on the stack were operating before, and it's actually more efficient for fans to operate at a lower speed. So if you run all 3 fans rather than just 2 of them, you can increase the efficiency of the motor that the motor is running at. And these 2 measures combined resulted in a 60% reduction in fan energy, a 6-year payback, and roughly 5% saving building energy use. Do you have anything else?
Well, it's way more complex. I mean, it's hard to fit it into a slide, but with the wind modeling, we had to add an anemometer to the roof of the building, which takes wind speed and direction. That is mapped and put into our BMS system. So we're constantly measuring the direction and the speed of the wind, and we're modulating the strobic systems to ensure that we have good dispersion and still maintaining duct static for the building.
On the subsequent buildings that we got away from that and mainly just went to the lowest best case scenario. So just for maintenance and
there was 2 different versions of the project. One was called simple turn down, where the cost of energy savings compared to the extra cost of having them modulate and and doing the further wind tunnel testing and mapping didn't have a payback to it. So we went away from the anemometers on buildings that were not going to benefit from it. And so we went to what's called a simple turn down, where it isn't the lowest possible, but there wasn't enough left on the table for us to spend the extra money to go down further.
So, the next thing that we looked at in this building is reducing the air changes. So early on in our design process, we had a technical guideline say that we wanted 12 to 14 air change hours in occupied and 6 in unoccupied. Through a lot of research and information, we decided to change UBC standard to 8 air changes and during occupied and 4 unoccupied. And that's what our new buildings are built at, but this one was still operating at 12 and 14. So by changing the air changes to our current standards, we were able to reduce makeup air by roughly 100,000 CFM. And this had a less than 1 year payback and fairly substantial energy savings as well.
This was all executed in-house with our group, so.
Yeah, this is, Bax Group did all of the implementation for this one. Here's the picture of the wind tunnel model that was made. I'll put this is in here. So that's Life Sciences building in wind model, small form.
The company is called CCP Wind, if anybody was curious. It's out of CCP Wind.
CCP Wind. So in summary, this is all of the energy savings projects that we've done in this building to date. There's actually an additional one on here. We've added some drives last year that's not, I didn't have time to put on here because we haven't M&D'd it yet. But you can see the CapEx for all of these projects is roughly 1.5 million. We received around $500,000 in utility incentives, $681,000 in grants. UBC's cost was only $240,000, but we've seen roughly $600,000 per year in cost savings. So our payback was less than 1 year. And yeah, that's how we got from 800 kilowatt hours per square meter to that roughly 400. We've half the energy consumption of this building on campus, and this is basically an example, the best example on campus for what we do to all buildings here at UBC with our BMS group and our energy conservation group. So the main takeaways from this presentation that I'd like to give is that it's possible to make significant reductions to building energy use through low and no cost measures, through basic maintenance, simple BMS control changes, and then having a dedicated energy team that can actually spend time to understand how the building operates. And that's it.
Well, the one thing I'd add to Julie's awesome presentation is that the story doesn't end there. Julie's crew and one of Zach's BMS technicians, who's a mechanical engineer with roughly 35 years of experience with BMS and engineering, is now doing a deeper dive into the building. As you can understand, with all these different measures, we've found through other projects that when you do many measures in a building, sometimes they compete against each other. And where you're looking at static reset versus air changes versus high plume exhaust, sometimes they don't necessarily get along with each other. So we're doing a deep dive into the building to see if there's further energy savings by examining the programming, looking at where things may not be what we believe them to be, and they're relying heavily on the SkySpark data and the fact that Justin did most of the energy conservation through some of the projects, except for the heat recovery chiller and the high plume. He did a lot of other energy conservation in the building, and so we're just going back, re-examining the building. And the interesting part is that it paid for itself, because even finding small incremental energy changes in that building due to its size more than pays for us to have an engineer dedicated to it for 6 months of the year.
Yeah, I mean, a really good example of that, not at this building, but Julie captured this. We did a air quality upgrade at Michael Smith Labs, and something very unexpected from my standpoint happened where the system was always driving into cooling mode for air changes as opposed to the air acuity minimum airflow. And Julie said, let's run the system at 12 degrees year, 12 degree discharge air from the air handlers year round. And the size of the air handlers basically captured large savings because the cost of cooling was quite a bit cheaper than the cost of fan energy in that case for the supply and the exhaust. So there's things like that where you can sit on the job for, Julie's team can continue to look at it for a year. My team can continue to look at it for a year, as opposed to a lot of times when you have an external contractor, you'll end up, yep, I met your specification requirements and I'll see you guys later.
Yeah, that's a really good point, Zach, because a lot of our energy conservation projects, when we do them like air acuity or heat recovery chiller, basically all of our projects require somebody dedicated at UBC to babysit the project to get it to work after the fact, to make sure that it's supplying the correct temperatures, that it's not tripping.
Yeah.
There's not the weird logic in there. And that's just, it's not a lot of time, but like, Justin, for example, will every morning look at it for half an hour and kind of see if everything's doing okay, especially in a transitional season like in the fall and in the spring. And
I love the chat. All right. So that said, do you guys have any questions for us?
That was a fantastic presentation. Thanks for fitting all that into a short amount of time. Years, decade or more of work, and you can see the results. So yeah, it's extraordinary. In the chat box, there's a couple questions. Amy asked for you to run through the team again. How many staff do you have working on energy?
Yeah.
Okay.
And the savings amount, it was $9 million? 90. That's that, yeah.
That's a cumulative energy savings. Roughly every year, we're avoiding about $9 million in energy use that counteracted the growth of the campus. 4 million electrical, and so it's 4 million. Sorry, 4 million.
Okay.
4 million.
It might
I
be
did the
9 if you
calculation.
include cost avoidance.
Yeah,
I haven't done my calculations.
So the energy team as it is, I can't take credit the way it was set up. That was Dave Woodson, our former managing director, when he, one of the issues with doing energy conservation anywhere is having control of the systems that you're trying to save energy on. And so what he did was he when we created the utilities department, he added the BMS department. And so that was taken part out of our building operations group that operates the buildings. And so it creates a little bit of a silo, but due to good working relationships, we keep it going. And so Zach's in charge of all programming and operation of HVAC systems within buildings. And the other half of our department, the utilities department, is responsible for everything up to the valve, supplying electrical, hot water, sewer, storm, domestic water, that cover everything, gas, to all the buildings. So we have our own infrastructure on campus. And so within the Energy Conservation Innovation Group is myself. Julie is the senior energy engineer who leads a team of 5. So there's 5 energy engineers, one's an ancillary energy engineer. And Julie, all of them have master's degrees in energy engineering. One of them's got a PhD in it. And then Zach's crew is Zach and 5 BMS programmers. And I like to brag about this. I know I shouldn't be bragging all the time, but within Zach's crew, for instance, they're all senior BMS programmers that I've managed to attract from various large companies like Siemens, Johnson, over the years.
With a PLC guy.
A PLC guy. And so we joke, but there's 140 years of controlled experience in the 5 guys that are in that department.
About 50% of what we do is energy related, and about 50% is supporting BO. So we work closely with our building operations group. If they have any complex problems, there's a few engineers over there, and we'll regularly support them. So like I said, about half of it is this system's doing something weird. We don't know what's going on. We have to support the BO guys. There's no heat in the building. Nobody knows why. We'll support that team for that. And then the other half is, hey, we need to make sure that all of these things are getting implemented properly. So it's kind of a half and half that keeps them happy, so they don't try to create a parallel team or anything as well, and make our lives quite a bit more complex when you have more than one person touching some of this code. That does get like very complex over time.
The one thing you may be considering when you're thinking, oh my gosh, they're 9 million square feet of core space and they've got 12 people dedicated to energy conservation. You have to understand that it wasn't 0 to 12 people. Yeah. It's been a slow growth to the department we have, and the cost avoidance or the energy savings a year is about $400,000 new energy savings a year. But then you think about how much we don't pay every year based on the energy conservation projects of every previous year, and our department is well funded, and we're a fraction of the cost of the energy savings that are reoccurring every year. And because we have the dedicated personnel on the ECMs, the industry standard is about a 10% degradation on any energy conservation that you do, initiative that you do. But we've kept it at roughly 0 degradation because Julie and her crew and the BMS guys are diligently watching the control systems and the result of our energy conservation projects, be it the high plume exhausts or heat recovery chillers, and they're looking at them and seeing where they are, whether they're not running, then we prompt that to building operations to get it repaired. We help them with the repair. We drive it as a project manager to make sure the repairs happen. And so I wouldn't expect somebody to open up a department and hire 12 people. We've gradually gotten to the place where we've gotten.
And I think one of the keys that Phil was talking about earlier is that having the utilities within our Department of Energy and Water Services is very important in funding our projects, because whenever we do an energy conservation project, that directly impacts our commodities budget. And so they see it on the utility side. And we are funded, we have a $500,000 a year funding that comes from the utility side to basically fund projects on my side per year.
That's purely for energy conservation projects.
Just for energy conservation. So I have $500,000. And then I have another, roughly we have around another $300,000 to $400,000 that we get in incentives from BC Hydro and Fortis BC programs. So it's all about $1 million a year that we spend on energy conservation in my group.
I was only going to say on that. The energy conservation also funds $200,000 in purely controls related upgrades that aren't driven by our deferred maintenance. So we can specifically target deferred maintenance items in buildings that have more of an energy conservation. So they wouldn't necessarily get to the top of the pile of things that we want to target because of age. But if they're going to enhance the energy conservation within that building, we will spend money on a control system up to $200,000 a year. And SAC has no problem, and Julie have no trouble spending my money. And they upgrade the project specifically to enhance energy conservation. So where an energy conservation project might not have the budget or the payback required, the 5-year payback or better, or the incentive from BC Hydro or Fortis, we will spend money on upgrading that control system to make the project better.
One of the other things that our group supports building operations in is doing building up controls upgrades. Like I've got a $200,000 budget, but I actually interact a lot with building operations when they're doing their things and drive it towards energy saving projects and such just by supporting them. So for example, we did a lab building that got turned over to us from a private group that was on campus. Sorry. We, as part of that, they were just going to do like a bare bones upgrade. And I said, well, look, since we're in here anyway, why don't we fix these pumps and put in some VFDs? And that allowed us to save, I paid for part of it, but it was a very small portion of, $60,000 of a $500,000 job.
I apologize. We're very, very proud of
all
what we
very
do here.
We're excited about it.
Do you have another, did we answer your question, and do we have another question?
I love that.
Yes, there's a couple. Thanks for those answers. I think they really get to the point. I think this next question from Jillian is kind of around that. What kinds of monitoring, metering, et cetera, are in place in this building and others, you can see, oh, we noticed this or saw this.
Yeah.
I'm sure that it's taken pretty intense metering and monitoring and maybe even some AI applications to identify those opportunities where you can take advantage.
I met with last week. Was it Trevor we met with last week? Who did we meet last week? It was in the meeting, in the preamble for this arranging this talk. It was really interesting because when we were asked of, what kind of metering we have, my mind and Julie's mind automatically went to, oh, they want to know what kind of buildings we do sub-metering in. And so we started going down to, well, we don't use a lot of sub-metering. And then the response was, oh, you don't have metering? And I'm like, oh, no, of course we have metering. But I just, maybe it's a little bit of the, I feel like we've been doing it for 5 years. Yeah. So one of the things that we have for almost every single building on campus is an electrical meter,
And
a gas meter,
So,
a district energy meter.
so every building has, if it's available or if it exists, we have a gas meter, an electrical, like main total electrical meter, ES, which is our district energy system meter, and a water meter.
Yeah.
And so that is like basically the minimum. Some buildings we don't have gas at all, so there's no gas meter. Some buildings we don't actually have DES, so there's no DES meter. But at a minimum, those 4 things, if they exist in the building, are metered per building.
Yeah, and it's basically impossible to justify these projects without building level meters because you can't do measurement verification to see if your project is working.
Yeah.
You can install temporary meters, you can look at schedules and see it, but it's really hard to see. And even before you get to doing energy conservation projects, you don't even know where to start because all you have is a campus level meter. And so how do you know what building's consuming the most energy? How do you know what buildings, like benchmarking is really the first step in this project. Get sub-meters on all of your buildings and start benchmarking them against each other so you know which ones you should be paying attention to. And then in terms of monitoring, we implemented a SkySpark system. We started implementing it roughly 3 years ago, 4 years. 5 years ago.
First year I started.
Yeah, and so all of our data from all of our energy meters and all of the BMS systems that have BACnet trend logs are basically imported into one centralized location, which is our SkySpark database. And we use that now. Everybody on our energy team, engineers and building operations use it. Our electrical engineers use it for figuring out which loads, for figuring out electrical loads where they can add more infrastructure. And it basically is a really awesome data visualization system. And that's what our data analyst works on basically full-time here, is maintaining that SkySpark system. It's almost worth us doing an entirely different presentation on SkySpark because it's really amazing. And before we had SkySpark, my job was so difficult because I'd have to set up the trends, wait for the trends to populate, download the trends, and they'd be in this ridiculous format that I'd spend like half a day trying to organize timestamps, like across different trend log points. And this basically is just like within a second, I can pull up 10 to 20 different trends on the same
synchronized.
Yeah, and they're all synchronized and it graphs it automatically. And that took away like days of work for all of my engineers, basically.
If anybody's, sorry, and yeah, and then we do all our M&D with it.
Well, I'm just thinking it allows you to also capture when Julie and I did a upgrade again at MSL for the heating system. Sorry, at a building. It's we started noticing, we're not getting the savings from 2 a.m. to 4 a.m. on Thursdays for some reason, and that allows you to quickly narrow it down as opposed to looking at a month's worth of data, even where you get a single meter reading for a month and it's like, we're only saving 30% of what we thought we were going to. It's like, we're not saving 100% for 2 hours a day. Anyway, amazing things for us. And allows you to
No, that's a great response, and I am curious to learn more, and I'm sure some of our folks are around SkySpark. I'm pretty certain that's the software that University of Calgary has been implementing through the fall. So hopefully
So we
we'll
talked
have a
about 2
chance.
years ago.
Excellent.
Good talk.
Touch.
Good turnout.
Another question that's come up from Amy at Bull Valley College is which institutions, oh, this is to the folks on the call. I'll ask this out to everybody kind of separately, maybe. Or maybe you can send in your responses. Everybody on the call can either put it in the text chat or send an email. Which institutions on the call have a dedicated climate action plan? UCalgary does. We're not sure about the other institutions, and we're looking at trying to do that. What does UBC's climate action plan look like?
Yeah.
And how does this all relate into it?
Yep. So UBC's climate action, the mandate has always been to go twice as far, twice as fast as anything that's been mandated to us through the province. And so our targets have been a 33% reduction in 2015 below 2007 GHG emissions. So 2007 is our baseline. So 33% reduction by 2015, 67% by 2020. And now we've upped our ante again, and we have to be basically 0% or near carbon zero by 2030. So we have 9 years to figure out how to make that happen.
So just to expound on that a bit, we are carbon neutral currently because we pay, on our commodities, we pay carbon tax. So all government institutions, all public sector institutions are in BC are mandated to be carbon neutral. So we all pay carbon offsets. So that wasn't good enough. And so one of the big jumps we went from is our antiquated steam system and boiler system in our power house. We went and replaced approximately, I think it's either 15 kilometers or 18 kilometers of steam pipe with district energy. So we went to a high temp, 105 degree max, Celsius max, hot water distribution system, replacing all steam heat exchangers or direct steam buildings with energy transfer stations. We did this about 7 years ago. 6 years ago, we kind of completed that process. And so that's what gave us the initial 33 or 30% reduction. The next reduction was we also have what's called a biomass facility. Ours is a gasifier. It was 4 megawatts and then 2 megawatts of heat recovery from a cogen system in the building. And then we just recently added another 12 megawatt biomass boiler to it, which should be firing up in the by the end of the month. And so that's contributing to another 33% reduction in GHGs. And so the thing that Julie's working on with her crew is we're currently working on with a consultant to do a decarbonizing our district energy system by 2030. And so that may involve many things from replacing the heating system with high temp heat pumps, buying more RNG to offset whatever residual gas we're using, as well as looking at other opportunities to lower building temperatures so we can go to peaking plants within buildings. So there's a lot to wrap around in there.
Yeah, so how are we pricing carbon for 2035 scenario? So we are forecasting the carbon tax increases that have been announced, I think, federally.
Yeah.
So it's going up to
about $140 or something.
140, is that it?
Yeah. I can't remember.
Anyway,
I think it reaches 170 or 180 by 2030.
Yeah, sorry.
So by 2035, it could be, higher than that, but it probably will be at least that.
So what's
internal?
Yeah, and then we have a internal carbon price that we've set at 250, which is a proxy price that we're supposed to be using to make decisions on. So that hasn't been fully flushed out yet, but we not only do we have the 170, but we also have to pay offsets, which are about $25 a ton on top of that. And then we have the proxy price at 250, which isn't really fully solidified how that's going to work out yet. But But I think the key component here is that if you do carbon reduction measures now, you are saving in cost avoidance for future costs. So if you save, 1 ton of carbon now, in 2030, that's going to be $170 that you're not going to have to pay out of your utility bills.
Is the district energy system hooked up to all the buildings on campus?
Over 100 buildings. So most of the buildings, yeah. There are a few buildings with their own boiler systems, but very, very few. I think it's in less than 5. Less than 5 buildings have boilers. The rest are district energy or have heat pump systems and backup boiler.
Yeah, so there's legacy for costing getting the piping into the building or when they were built.
Yeah, I'm going to jump back to a previous question here about building metering and how it was done. So the building metering was all done through in the early 2000s as part of the EcoTrek project, and it was funded by that. And that was an ESCO project where I think MCW actually paid for all of it, and then UBC,
Guaranteed savings.
Yeah, guaranteed savings, a guaranteed savings program, and then we paid back through an amortization through the savings. So that was actually funding that was provided to us to do the project, and then we paid back that loan through the savings. So the metering was done hand in hand with the original, with the original kind of scratching the surface, scheduling, set point changes, that kind of stuff.
And then it's continued on from there. Once you dip your feet into putting meters in buildings with the district energy system, the energy meters were part of every single install. So every building, the cost of that project ensured that we had a meter in that building. All new buildings have meters with them. So it's part of the design criteria is that we supply your meter for you, you pay for it. And that one thing that I could comment on that is it's good to standardize on meters. So we've standardized on our hot water energy meters. They're all Camstrup meters. We've standardized on all of the electrical meters. They're all Schneider electrical meters. And we also have an ion system meter, ion system that collects it through Schneider. So standardizing helps lower the life cycle cost of everything, because then you don't have to have multiple vendors on campus. You can find something off the shelf that's one brand and multiple suppliers.
For the Camstrup, we got lucky in that we defined it so it goes into our district energy metering. We've also got it going into the BMS system, allowing the building itself to use that information. So again, once you get that standard in, we've got one meter that isn't standard, and it's the only one that's not online. So.
And I'm sure it bothers you. I can see
it drives me insane.
And those meters, are they like Bluetooth or those kinds of things, or are they kind of hardwired?
Hardwired. Everything's hardwired. So there's no such thing as good control over Wi-Fi.
Yeah.
And so everything is connected through a master meter in the building into the ion system. Within some of the metering, or all the hot water meters, the district energy system meters in the building are all through a field server that does Modbus to the ion system, simultaneous to backnet into the BMS system.
So yeah, for that sort of thing, because we are using the data, number one, from a historical trending standpoint, the hardwire is just more reliable, and additionally, we use it for building load. We didn't end up with the DES. We do limit the maximum flow through the heat exchangers, and so it is like a critical piece of data in order to limit the valve positions and such on the system. But because of the criticality of it, hardware.
No, that makes a lot of sense. I'm curious in learning more about that process, because I know it's of great interest. It's been tough for our institutions to find the funds to do the metering. They know they want to do it. And the ENSO model it's kind of been thrown out there. So I don't know.
When you're doing the core meters, it's pretty.
Yeah. I was going to say a meter itself, based on the energy data that you get out of it and the energy conservation you can then do in the building, a meter will pay for itself easily.
Yeah.
And so it's just taking the first step. You have to get the buy-in. So part of the process here that we've always had is we've always had a lot of upper management support on our initiatives. And so you have to develop those relationships. And we go through this, it's kind of funny, we go through with our BC Hydro, like some of our funding from my position and a few other positions in the department comes from BC Hydro, that we have to go through this SET program, Strategic Energy Management Plan. We do it every year. And it's ironic because the biggest thing on when you take the Strategic Energy Management Plan program is they talk about getting buy-in from upper management. And they say, and I always tell them, I said, my smallest problem is getting upper management support. My biggest problem is trying to get all the jobs that we need to do and all the money we have installed in 1 year. And I know that's kind of gloating, but we're a victim of our own success in a lot of ways. And so it's our biggest problem isn't the funding. Our biggest problem is just where do we start?
No doubt. There's a question here. What are the fuel combinations you're using for the biomass system?
Yeah, so the biomass system uses only waste wood products.
Post-consumer waste wood.
Post-consumer waste wood products from
Furniture.
furniture, the pulp mill waste wood that would have otherwise gone to a landfill. It gets amalgamated at the Cloverdale fuel station. Thank you. It's like 60 kilometers away, and then it gets trucked in and used in our biomass.
We have a lot of sawmills, obviously BC forest industry. So we have a lot of post waste wood from wood mills, pulp mills, and construction waste.
Excellent. Wow, there's a lot going on your campus. I'm not sure if there's any other questions. We're actually, well ahead of time. We got through a lot very quickly, so I certainly appreciate that. And I think there's going to be more opportunities. I mean, I hope you guys are available to follow up. You've put lots of bugs in our heads of projects you guys have had that we can really learn from. And so, really appreciate your time took to put together this, to show up and help us understand how you've gotten where you are. It's been a really great journey, and really.
I think if you want to know anything more about the technical specifics, you can probably get in touch with us. I'm okay. I always like talking about controls and such. So.
Yeah. If you want any information on what the metering, how the metering schematic is for a building, we can send you what we currently use, and I'll give you a rough schematic of it. If you want to know if you want to have the framework of how we work, I can send you an org chart and discuss that if anybody's interested. And if you want us to come back, not necessarily right away, but at a future meeting and do a how did we afford to do SkySpark and what benefit is it doing, we can do that certainly for you.
And additionally, the why, because like a lot of times you'll get vendors telling you that, oh yeah, we can do this. Like when you set a Bluetooth meter right away, I'm sure somebody's told people that, yeah, no, Bluetooth, this is great, it's going to solve your problem. The cost of putting the wire in isn't the expensive part of the meter, and it is the part that guarantees reliability. So that's why we've gone that way. And all of these things have reasons why we've done it. We're not generally just doing it. SkySparks as well. It's like, why did we go with SkySpark? There's a bunch of reasons. How did we approach connecting it to our data sources? We did a bunch of things, and there's some things we'd probably do different if we were doing it again today, but there are reasons why we did it that way originally. So yeah, obviously there's all the historical reasons why that are important as well when you're making your decisions, I think, because you don't necessarily have the same backgrounds as us.
That's such a great point. I mean, just by going through it doesn't mean that it's all gone perfectly, but the fact is, if we can learn from those and step on your shoulders and avoid some of those issues and learn from each other, we're all going to benefit. So really appreciate being that transparent. No, and we'll certainly be in touch. Does anybody else have any other questions from the group, or is there any other things we should cover?